Hi. On the board and theory class, I gave you three potential power supply circuits. They were all based on the Dell laptop. This is the solution for the full wave version of that. It's not for marks, but I can promise you'll be seeing this circuit again. Here's how it would work backwards. We knew we had 19.5 volts on the output, and we had 120 volts RMS plugging into the wall. We said, what's inside there to make this work? And I gave you a few of the steps, but if this is VDC out, in other words, this is the output of the power supply, we kind of got to start there and work backwards. We know that VDC average, and I'll write this down now, VDC average is equal to the peak output, because it's a full wave, times 2 divided by pi. The problem we've got is that what we want is this guy, right? So we need to manipulate this formula. For those that aren't comfortable with this, I know there's always some. I'll do it in steps. What I like to do is get the variable I'm looking for on the side where I want it to end up. So oops, that's pi. Right? Now I can start working with it and say, okay, first thing I'm going to get rid of, let's say the pi. So I'll multiply both sides by pi, and then I will divide both sides by 2. What that means is V peak out equals VDC average times pi divided by 2. Throwing some numbers into this, VDC average was 19.5 volts. Obviously, pi is 3.14 and 2. When you run all that, I believe my numbers came in at 30.6 volts peak out. So that's what's coming out. All right, so that's V peak out. That's sort of the first step. So that means that across this resistor, our peak output is 30.6 volts out. Now we can sort of work backwards trying to track down the secondary voltage and then eventually get a transformer ratio. What maybe I'll do is, knowing that that's a solved number now, I'll put anything we solved for up here and say V peak out equals 30.6 volts peak. Okay, now the next sort of step in this process is saying, what's the secondary voltage? Well, if you remember before, if we were looking for V peak, we took V peak secondary, divided it by 2, and subtracted 0.7, right? That's how we were finding the output voltage. So in our case now, what we're going to need to do is, again, spin this around to find this V peak secondary. Again, for those that aren't 100% comfortable with the idea, I'll run through it in partial steps. V peak secondary divided by 2 minus 0.7 equals this output. Remember, we're trying to find this V peak secondary number now. So we can start eliminating things. We can first do plus 7. So we could say V peak secondary divided by 2 equals V peak plus 7. Right? I've added plus 7 to both sides, eliminating this. Right? Now I want to get rid of the divided by 2, so I need to multiply by 2. So V peak secondary is equal to V peak, and we're going to multiply it by 2. That's our secondary voltage. And if I put numbers in there now, what did we have? V peak was 30.6 plus 0.7, right, times 2, which means our secondary voltage, this is the voltage in the secondary, complete secondary of the transformer, was 62.6 volts peak secondary, right? So now we've got that number. So we are making progress here. We now know the entire secondary voltage. And again, maybe what I'll do is put that up here. I'm going to run out of space, so I'm going to try and... Secondary was 62.6 volts peak, right? Now what we're after, I suppose, would be the ratio, right? So what type of center trap transformer do I need? Well, if we're looking for the ratio, we could say that we know for sure in this ratio the secondary voltage is 62.6 volts peak. What's this primary voltage? We've done this in class, I'm not going to do it again, but we know for sure there's 120 volts RMS. If we convert that to peak, we know that the number is 169.7 volts. So if we're trying to find the ratio, if we take 169.7, we divide it by 62.6, what we end up with is the ratio on this transformer being 2.71 to 1. So that's the ratio that we're going to need to get this to work. 2.71 to 1 is our transformer turns ratio. The only thing we really haven't solved for here was that peak inverse voltage. We still need to sort that out. And if you remember from class, the peak inverse voltage was V peak out. So the entire, what the voltage coming out across the load resistor is. Remember we went times 2. The idea was that we're now doubling that. But remember, this voltage here was 0.7 smaller than the secondary. So in order to make it work, we have to add back in one of the two diodes, because one's forward bias, there's only one in the circuit when we're calculating peak inverse voltage. So for peak inverse voltage in this situation, this would tell us what size of diode we need. We're going to need to go 30.6 volts peak times 2 plus 0.7. So the output voltage, peak, times 2 to give us the secondary voltage, but remember now we're down 1.4. Add in the one diode that's forward conducting, and the result is, I have to 61.9 volts peak. So that's what the diode has to hold back. If I had, the only other thing that we probably could have calculated here is if I had given you a load resistor, we could have figured out the forward bias current and then gone to some spec sheets and come up with the exact diode, knowing how much it has to conduct forward, how much it has to hold back backwards, and you could actually go out and buy components and make that power supply yourself. Hope that clears everything up. Thanks.